Good afternoon, Professor.
Hi, Najar. How are you doing?
Good, preparing for finals. You?
Actually, also soon need to prepare for finals, need to prepare some problems.
Are you going to prepare problems for our finals or?
Yeah, I mean, not only me, all instructors.
Got it.
Yeah.
I just saw that only one Professor Sergey Bubin is preparing problems. Like
No,
at the
he uploads them. So his responsibility to assign problems to students in long kappa, but every instructor has to prepare some problems within certain topics which are distributed between us, code the script for these problems with different versions, and then send it to Professor Bubin. And we have some discussions on these problems, and finally they are uploaded in long kappa and assigned to students. But that we do only for midterms and final exam. For homework assignments, these problems are picked up from the database available in long kappa, and there are just few instructors who are responsible to check them before they are assigned to students.
Professor, also, can I ask one quick question about finals?
Sure.
Is the format of final exam similar to midterm, or there are any differences?
Yeah, it will be similar, but most likely it will be longer, so you will get more problems for final. But other from that, it will be the same.
Okay, thank you.
Okay, guys, nice to see you.
Can I ask a question?
Yes, sure.
Regarding our grades, will there be curved? I mean, the plank between, for instance, for the grade A, it will be lower.
So at the end of semester, there will be, we will see with what we deal. All instructors will have meetings, and final decision will be made for, like, regarding this. So of course it will be applied to all students equally. Could be that if the picture is okay without curving, we will not apply curving, since it's kind of favorable approach because there are too many students for that. But we'll see how it goes.
Okay, thank you.
Yeah, I cannot be more specific.
Can I also ask you about the difficulty of final exam? Will it be the same?
I think it will be similar to midterm 3.
Okay.
It will be, I'm quite sure there will be more problems, and also as a result, you will get more time to deal with this. But there will be a mixture of, let's say, some simple problems and like middle level difficulty problems.
Okay, got it. Thank you.
Something like that. So this midterm 3 actually was better than in average than midterm 2, like noticeably better. Still could be better, of course, but no limit of perfection. But for sure, midterm 3 was done noticeably better. Okay, good. Then we continue our discussion, since we have quite a lot to discuss in this field of thermodynamics, and unfortunately we don't have much time for wait, somehow it used to be, oh. Okay. So during our previous discussion, we considered relationship between macroscopic parameters like pressure and temperature, and microscopic parameters which quantify some features and properties of molecules which create the ideal gas under consideration. So this is done in the framework of kinetic theory of ideal gas, and we got some relationships between pressure and average of square velocity, direct relationship between temperature and kinetic energy of molecules. In particular, that discussion was carried out in the scope of the model, which considers monoatomic ideal gas. So today we continue to consider ideal gas with more focus on, also in the scope of kinetic theory, but with more focus on molar heat capacitance of this ideal gas, which actually we will show that depends on the process. So it's not the same for different processes. For instance, for isovolumetric and isobaric processes. So let us consider a system like some ideal gas. We have this volume and pressure. Then we have two isothermal curves, which corresponds to constant points, and these curves correspond to the same temperature. So we have T and some T plus delta T. This is two isotherms for two different temperatures. And then we consider some initial state and different processes which can cause the change of the temperature of the system by delta T. So actually going from one isotherm, like first isotherm, to the second isotherm. But this process can happen in a different way. So let's say we have something like this. It's initial and final state. Then we have something. This will be some other final state prime, and then something like this. final double prime. So in all these processes, change in temperature is delta T. However, the processes will be different because different work will be done in different processes. So we will consider two processes, isovolumetric and isobaric. So since change in temperature, delta E, is the same for all processes, then for all processes, a change in internal energy will be also the same. We know that internal energy is, as was shown during the previous discussion, directly determined by temperature of the system. So the same change in temperature results in the same change of internal energy. And let us consider these two isovolumetric and isobaric processes. In these cases, since we deal with some number of moles to describe the quantity of material which we deal with, then it's convenient to operate with so-called molar specific heat CV and CP, which correspond to isovolumetric and isobaric processes. So some heat Q will be equal to mu number of moles times CV times delta T for the case of constant volume. And also heat can be represented as product of mu Cp times delta T for constant pressure, isobaric process. So since here is an important moment of this regarding this CV and CP. Since at constant volume work is not done, so work is equal to zero because delta, like change in voltage, is equal to voltage in volume is equal to zero. Then all energy which is transferred by heat to the system goes to increase of the internal energy according to First Law of Thermodynamics. And thus it will cause certain change in temperature, delta T, at volume constant. Then if we have isobaric process, then we have a bit more complicated case, because in this case voltage is not constant and means that some work will be done by the, let's say, expanding ideal gas. Since we keep pressure constant, if we provide some heat, we increase temperature. And in order to keep pressure constant, we need to increase volume. So some work will be done. That means that if we provide the same amount of heat, like energy via heat, it will go to change of internal energy, certain change, let's mark it prime here, and plus some work done by this expanding gas. this change in internal energy will be smaller than in the case of isovolumetric process, because obviously part of energy transferred by heat will be spent for performing this work. And this delta T prime, which is observed like increase in temperature for the system at pressure constant, will be smaller than delta T under the isovolumetric process. So that means that with providing the same energy by heat, we will observe smaller change in temperature for the isobaric process. And this statement brings us to the conclusion that Cp, molecular heat, specific heat capacity of ideal gas, should be larger than Cv. So this we so far keep in mind, and we will come to this further, but just to understand and draw your attention to this physics behind the statement that Cp larger than Cv. That is because we involve this additional work done by system at isobaric process. Now let us proceed with determining value of Cv first. Let us consider first volumetric process. So let us define again total internal energy, which for ideal gas could be considered as total kinetic energy, and it is equal to 3 second times n total number of molecules, kT. I don't write here B, just to keep it more clear, the equations. So you remember that K is Boltzmann constant, so we don't specify it now. If we use some other quantity which is marked as K in future, we will mention about this. But so far we just skip this B and write just K. So it will be 3 second n times kT, and it can be also represented via the number of moles and ideal gas universal constant, which will be 3 second mu r t. So this is total like internal energy, and assuming that we have monoatomic particles of ideal gas, which have 3 degrees of freedom, and only kinetic energy of translational motion is taken into account. We will again come back to these degrees of freedom and discuss them a bit more details quite soon. But so far we consider just monoatomic case. So now let's assume that we have some constant rate of providing energy to the system by heat. So constant rate could be defined as heat divided by some time interval. So this is constant. And in case of isovolumetric process, work done on the system, because it can be either expanded on or compressed. So let's say work done on the system, integral P times dV is equal to 0 because we don't change volume. Then all energy provided by heat is causing change in internal energy. So in this case, we can write that change in internal energy is equal to nu times CV times delta T. So this is equation which gives us relationship between change in internal energy, assuming that work is not done, and specific like molar heat capacity under constant volume, CV. So let us write it on the next slide and proceed further. So change in internal energy equals to nu times CV times delta T. So from here we can express CV and assume some very small changes in internal energy and temperature. So then it will look like this. CV is equal 1 over nu d internal energy over dt. And now we can substitute expression for internal energy in terms of universal gas constant and temperature. It will be 1 over nu. D of this expression will be 3 second nu RT over dt. So we have differential of this equation, d for internal energy, but here we nu and r, they are constant because we don't change the amount of material we deal with during this process, and we all like r is constant by definition. So we can take this like factor out it from the differential. Will be 3 second nu r dt over dt. And here I forgot 1 over nu. So nu and nu we cancel out, and also dt cancel out. So we end up with 3 second times r. So this is the capacitance of ideal, like molar heat capacitance of ideal gas under isovolumetric process. We know what is the value for universal gas constant. That's why we can calculate that CV is equal to 3 second times R is equal to 12.5 joule per mole per Kelvin. So this is true for mono, like atomic ideal gas. Just to remind you so far. Later we'll come back to this again. So now let us consider, we defined this parameter. Now let us consider the second process, which is isobaric process. In this case, pressure is constant, and change in internal energy is equal to heat plus some work done on the system. So in this case, it will be also mu times Cp times delta T. This stands for heat in this isobaric process, and that's why we use Cp plus some work done on the system, PdV, or delta V. So since, as we mentioned at the beginning, change in temperature for both processes is the same, change in internal energy is also the same. That's why for, as we defined earlier for isovolumetric process, the internal energy, change in internal energy is equal to mu Cv times delta T. This will be also true for isobaric process because change in internal energy is equal for both processes. So that's why we can write from the, so consider again this first law of thermodynamics. In the left side, we can write this equation. It will be nu times Cv times delta T. It will be equal to mu Cp times delta T. And now we need to do something with this work. So what we want to do, we want to express it in terms of ideal gas universal constant also. So for that, it's convenient to write equation of state for ideal gas, which is equal P times V nu times RT. And then for following this dependence, we can write that P times delta V is equal to nu times R delta T. That's why we can substitute, instead of work done by the system, this product of three quantities. Then we will have minus nu R times delta T. So let us put it in some frame. So now we have this equation. So what do we have here? We can get rid of nu. Also, we get rid of change in temperature. And finally, we get relationship between Cv, Cp, and R. So Cv is equal to Cp minus R. And usually it's written in a bit different form. So it's Cp minus Cv is equal to R. This is important relationship between molar heat capacitance of ideal gas at isobaric and isovolumetric processes. What is important that this relationship is true for any ideal gas, regardless if it's monoatomic, diatomic, or is based on molecules with more atoms involved. So why? Because the difference between them is caused by work done on the system from the side of environment, which is here or here. And this work does not depend on the molecular structure of ideal gas, regardless if it's monoatomic or multi-atomic. The difference between Cp and Cv always will be equal to R, which is universal gas constant. So taking into account that, as we have shown before, Cv is equal to 3 second R, then we can write for Cp it's equal to Cv plus R, and this is 5 second R, which is 20.8 joule per mole Kelvin. Again, this is true, this value for Cp, which is 5 second R, is true only for monoatomic gas. However, the difference between Cp and Cv for any type of mono or multi-atomic gas will be equal to R. So now there's another quantity which is related to this Cp and Cv, so-called adiabatic coefficient, gamma. We will talk about adiabatic process right after this quantity is defined. So it's equal to the ratio between Cp and Cv. And this is like, will be 5 second R divided by 3 second R. And this will be 5 third, something like 167. This is true again for monoatomic gas. So now we need to consider another important class of processes which can happen with ideal gas, and this is adiabatic process. So adiabatic process, by definition, we shortly mentioned it before, there is no energy transfer by heat between system and environment. So Q is equal to 0. What is the reason for that? It's either some perfect thermal insulation or some huge volume of the system, but our process is very fast, and that's why it doesn't have enough time to let this process, this energy transfer by heat to happen, so it can be negligible. Q can be negligibly small. However, we have this definition that Q is equal to 0. So in this case, temperature is changing, pressure is changing, and volume is changing. So all the state macroscopic parameters are changing, and we want to figure out what kind of relationships between these parameters will be for adiabatic process. So according to the first law of thermodynamics, change in internal energy is heat plus work. Heat is equal to 0. So change in internal energy will be defined by work done either by system or done on the system. Again, we know that let's deal now with some small changes in internal energy, the internal energy. So we know it defined by the product of nu Cv dt, and at the same time it's equal to work done on the system. Let's say P times dV. So from here we can determine like express dt, and later it will be used by us. So let us express dt. dt is equal to minus p dv divided by nu cv. So this is expression for small change of temperature based on the first law of thermodynamics for adiabatic process, assuming that Q is equal to 0. So now, since all parameters are changing, it's good to take a total differential of the equation of state of the ideal gas. So again, we come back to P, to this equation of state of ideal gas. P times V is equal nu times RT, and total differential, assuming that all three state parameters are changing, that is like taking derivative of, let's say, taking differential of the product of two functions, will be P times dV plus V times dP, and this is equal to nu R, which are constants, dt. Okay, so now it is good to substitute this change in temperature, because let's say we want to have to figure out how pressure and volume will depend on each other for a adiabatic process, but we don't want to deal with the third state parameter. So for that reason, we want to substitute it with its expression in terms of pressure, voltage, and molar heat capacitance, CV. So now we do this substitution, and we will get the following equation. Can write here, will be P dV plus V dP equal to nu R, then will be minus P dV divided by nu CV. So this will be equal, this we cancel out, and will be minus R divided by CV times P dV. Okay. So now we recall the relationship between Cp and Cv. So we derive this equation that Cp minus Cv is equal to R, universal gas constant. So what can we do with this? We can substitute instead of R here in denominator with Cp minus Cv. So let us write this equation again. It will be P dV plus V dP equal to minus. Now instead of R, we put Cp minus Cv divided by Cv. Maybe we can put them in common parentheses like this. P times dV. Okay, now let us divide everything. We want to get voltage. So let us divide everything by product P times V, left and right side. So let us do already this on the next slide. Need to rewrite this equation. No space P dV plus V dP equal to minus Cp minus Cv divided by Cv times P dV. Okay, now we divide this by P times V. And what we get will be dV over V plus dP over P equal, this in the parentheses is equal to 1 minus so all these parentheses with the sign will be 1 minus gamma, which is 1 minus Cp divided by Cv. So it will be Cp divided by Cv minus 1, but we have this minus in front of the parentheses. So we will have 1 minus Cp divided by Cv, which is 1 minus gamma. And that we defined previously. So now it will be 1 minus gamma times dV over V. Okay, now we come to some layer differential equation, and we just need to move this term to the right. Then it will be dP over P equal to just gamma dV divided by V, because we will move this to the right, it will be minus dV over V. So we will get rid of this unity here in the parentheses. And now by integrating this expression, like this differential equation, we get natural logarithm of pressure plus gamma times natural logarithm of volume, and this will be equal to some constant, which we get because of integration. And from here, taking into account the properties of natural logarithm, we know that sum of logarithm or natural logarithm is equal to the logarithm of the product of parameters under logarithm. And if we have some coefficient in front of natural logarithm, it is some power base of logarithm in power of this coefficient. So taking into account these features of logarithm, we can write that p times v in the power gamma is equal to constant. So this is the relationship of pressure and volume for adiabatic process. And let us maybe also draw some plot for volume and pressure. Show also two isothermal curves. And let us have some initial state here, final state here. And adiabatic process is something like this. So since gamma is larger than unity, because we remember that for isothermal process, we have P times V equals constant. For T equals constant. So since we have here P times V in power of gamma, and gamma is larger than unity because Cp is larger than Cv, then this adiabatic process is steeper than isothermal process. It happens, this change of pressure with change of volume happens faster. And in this particular case, when we have our initial case at smaller volume and final state at larger volume, so delta V is larger than 0, then we cool down the system during this adiabatic process from temperature T plus delta T to temperature T. We reduce internal energy of the system during a adiabatic process by performing some work against the environment. So for this particular case, it is also, and of course, the product of state parameters considering this relationship, like we have P initial, V initial in power gamma is equal to P final, V final power gamma. Also, another thing which can be shown for the adiabatic process, considering this equation for the state of ideal gas, the relationship between other combination of state parameters. So for adiabatic process, the following statement will be also true. Temperature times volume in power gamma minus unity is also equal constant. So we have two equations which relate state parameters which are changing in ideal gas during adiabatic process when energy transferred by heat is equal to 0. And with this combination of two equations, you can pretty much determine any unknown parameter which is necessary to calculate in the framework of different problems which deal with adiabatic processes. Okay, so today we discussed the introduction of molecular specific heat capacitance for isovolumetric isobaric processes, found relationship between these parameters, that difference between CV and CP is always equal to R for all ideal gases, regardless of structure of their molecules, and also in details describe the processes which like change the relationship between state parameters of ideal gas during adiabatic process when all state parameters are changing, temperature, voltage, volume, and pressure. And by definition of adiabatic process, there is no energy transferred by heat. So next, we will continue with this equipartition of energy, which takes into account molecular structure when we have monoatomic, diatomic, and some multi-atomic cases. But of course, we will focus mostly on example of diatomic case, and we'll show how total energy will be defined in that case, not only by kinetic energy of translational motion, but also there will be some contribution from rotational motion and vibrational motion. Okay, thank you very much for attention. Today, I think we are already out of time.
Thank you also.
Can I ask some questions?
Yeah, sure.
In the last step of differentiation, like in dV divided by V, let me.
1 second.
In dP divided by P equals to gamma multiplied by dV divided by V.
Yes.
Isn't there a minus sign before gamma?
Okay.
Like because
Yeah. Minus sign before gamma. Yeah, looks like you're right. We should.
Yeah, it's like 1 minus gamma minus 1.
Yeah. 1 minus gamma minus 1. Yeah. Minus gamma. Okay.
Okay, and next question is about at the beginning of differentiation, you said that change in internal energy is equal to you obtain change in internal energy as either volumetric change, like mu CV dt.
Yeah.
And you did it because we could actually use also like isobaric like mu Cp dt, but
No,
Ah, no?
Because if you use isobaric process, then this will be defined. So this product mu C whatever V or P delta T is the definition for heat, like amount of energy transferred by heat. And in this in the case of isovolumetric process, this heat is equal to change directly equal to change of internal energy. However, for isobaric process, this heat is not equal to change of internal energy because there is some work involved. That's why to be consistent, we always use and make our life actually easier. We always use define change in the internal energy via the product of mu times C V times delta T because it is valid since all these processes which are happening, they are by definition of our first figure, where it is, yeah, here, they all are happening between two isothermals. And that's why change in temperature is the same for all processes. If change in temperature is the same for all processes, then change in internal energy is the same for all processes. And that's why we can use mu CV times delta T as definition of change in internal energy for all processes which we consider today.
Okay, but isn't there a contradiction? Because like, I'm talking about adiabatic process where we said that mu CV dt is equal to minus P dV. Like, we use isovolumetric equation and stated that it's equal to work when the volume changes.
Yeah, I mean, so I see your point. So it is in this particular case, we don't need to be specifically attached to some boundaries which are set by the conditions in terms of voltage, so volume is changing or not. It is from point of view, like mathematical point of view, we have the right value of change of internal energy given by this product, mu CV delta T. And then we don't need to consider that this CV is for isovolumetric process. We deal with this like some number, which is for sure true because it's equal to all processes. And we just, it's convenient to use it to derive further equations because we, instead of having some unknown quantity, which is delta internal energy, it is given in terms of parameters with which we operate also in the right side of the equation. It's mu and delta T. So we can cancel them out and then get some useful equation. So it's just mathematically, everything is correct.
Okay, thank you. Thank you very much.
Yeah, you're welcome. Okay, thank you for attention, guys. Have a good evening and see you on Friday.
Thank you also. Can I ask you one question?
Yeah, sure.
About long kappa. Do we have the last week assignment this week? And the next week will be only the final exam.
Good question. I mean, this week you for sure need to have. So you have home assignment. this week. Most likely, this is true. Most likely you will not get home assignment for next week. But
Okay.
I'm not 100% sure about this.
Okay, thank you. Anyway, thank you so much.
Yeah. Okay, you're welcome. And yeah, guys, see you on Friday.
Okay, goodbye.
Bye.